Hello, everybody. Sorry, I was sort of stuck on another line there. So now for our seminar series with Aurelien Verdier today. So Aurelien obtained his master's degree in physics in 2020, I believe. During his stay at EPFL, he was quite active. He was the president of the astronomy club Calista, and he participated in two interdisciplinary projects, the radio telescope project and the space situational awareness project. I'm right?
Yep.
Probably. And then we hired him as a national trainee and sent him to Spain for 2 years. So if people don't know anything about the European Space Agency in Spain, it's called ESAC, and it is the window upon the universe. So Aurelien will be presenting the Euclid mission today on the solar system objects, and I recommend you, if you see him one day in person, to not get in a sword fight with him because he is an extremely good fencer. So there, the floor is yours.
Thank you, Martin, for this presentation. So yeah, my name is Aurelien Verdier. I'm currently a Swiss National Trainee here in Madrid, so close to Madrid in Spain. And today I'm going to talk about the solar system object pipeline for the Euclid mission. So I already had a good presentation from Martin, but just to specify, my master work was about HIRAX, which is the one of the radio interferometer developed in South Africa. And so now I'm working, after this, I directly went for the National Trainee program. And now it's been 2 years I'm here, and my contract will end in 2 weeks. So it's kind of nice now to finish everything, to present you everything I could do for 2 years as a Swiss National Trainee. So the small plan of the presentation, first I will present a bit the Euclid mission, because I think it's a marvelous mission and we need to talk about it. Then we'll talk about solar system objects. What are they, where are they, and why do we need to detect them? Then talk about detection methods. Then the pipeline we're using here at ESAC to detect them, and then have a final list of SSOs. So you will hear me saying SSOs instead of solar objects all the time, because it's kind of long. And then I'll talk a bit about the work life at ESA to make you maybe join the YGG program if you just finish your master and you're looking at this presentation. So let's go into it. So here is Euclid. It's a space mission. So it will be a telescope sent into space. It's a 1.2 meter mirror. It will be a 6 years mission. And this is what we call a survey mission. So for 6 years, we just map the sky. And then at the end, we will have, well, during the mission, at the end, we will have all the data available for anyone. The surface is 15,000 square degrees. And it will be located in the Sun-Earth L2 Lagrange point. I will show you after this for the people not knowing what are the Lagrange points. And there will be two instruments. First one for visual, which is this, and the second one for near infrared, which is NISP. The launch is now official. We had some trouble with the launch date. And the launch will be in July 2023 with a SpaceX rocket. So finally, we can launch Euclid, which is a very good news. And the science will be mainly dark matter, dark energy, with weak lensing, bionic acoustic oscillations. And in between all of this, we have SSOs. So yeah, just to show you where is L2. So maybe you know the James Webb Space Telescope. It will also be there. So as you can see, the second point is here. It's a gravitational equilibrium in between Sun and Earth, and we can send some space telescope there. They will remain in this point. So it's kind of useful to send stuff there. About the survey operation, here is a picture to show you everything that Euclid will look at. So this is the whole sky. You have to see like this is the whole sky, and all the colorful squares means this is where Euclid will look at. So you can see the dark spots are where we have the ecliptic latitude, so where the sun and the planets are, where our solar system is, and the galactic latitude, so where is our galaxy. So as we want to look at other objects than our galaxy and our solar system, Euclid is made for this. We don't look at this, we look outside those two objects. So this is what we will look at. I will ask you to remember this picture. We'll come to it later because it's kind of important for solar system objects. About the two cameras, so as I said, there is two. There is VIS and NISP. So VIS is about visible, so looking to the blue, red, yellow, red, like Hubble did. And there is NISP, which is near infrared, just after the red. And it will be a spectrometer and a photometer. I've been mainly working on VIS data, so I'm not an expert in NISP. So sorry if you have a specific question about NISP, I might not be the correct expert for this. The field of view of Euclid will be, so for one picture will be 0.57 square degrees. And the two cameras will look at the same part of the sky at the same time with different precision, we'll say. So this is very precise with 0.1 arc second. NISP is less precise, but as it is spectrometry, it's not a problem. And it will look like this. So the camera will be made of 36 CCDs. Each CCD is 4,000, around 4,000 times 4,000 pixels, so it's very huge. And even this CCD is then 36 CCDs, so it's a lot of information in only one image, but it's not over. When we will be doing the mission, we will move a bit the camera. So there is what we call dithers. So the first dithers correspond to the first 36 CCDs I showed you. And then there will be a small shift for the second dither, and again another shift and another shift for the remaining ones, just to fill the gap in between the CCDs. So at the end, we get a beautiful picture without any holes for Euclid. Unfortunately, we still haven't any picture because the spacecraft is still on Earth, so I won't be able to show you beautiful pictures like Hubble or the James Webb. We will have to be patient to see those kind of pictures. The observation sequence, so what we will do in each dither. So it's separated in different blocks. So block 1 corresponds to dither 1, block 2 to dither 2, and so on. And each block will be separated by around 1,000 seconds. During those 1,000 seconds, a lot of stuff will happen. In parallel, we will have this starting to take a picture, and we will have NISP starting to do the spectroscopy. And then after this, use near infrared filters. So they are named Y, J, and H, and they will proceed to do some pictures too. So everything will happen for each dither. So at the end, we have this picture times 4. So as you can see, we will have a lot of information in only one picture. So this is the main reason Euclid has been saying, is to have a wide information about space. For example, if we come back to James Webb, it's about having deep information, very precise information. With Euclid, we'll have wide information. So where galaxies, how they are located and stuff like this. So this was about Euclid in general. And now I would like to speak about my work, which is about solar system objects. So what are they? It's another name to just say asteroids, but maybe we will find other objects than asteroids. So maybe we still have the name solar system objects to mean, it means that it's objects located in the solar system. So we are looking at very close objects with a spacecraft that is supposed to see objects very far away. I will come to that later. So where are those asteroids or SSOs? So of course, we have some close to Earth with the near-Earth asteroids, or to Mars with Mars crossers. You should know, I think, from school that we have the main belt asteroids just in between Mars and Jupiter. We have some, I don't know, I think it's kind of funny to have these asteroids just on Jupiter orbits that are a bit stuck there because Jupiter and the Sun have also the Lagrange point. So you have some stuck asteroids just there. And even further, we have also, again, asteroids just going through the Jupiter orbit. And we have this Kuiper belt object, which is kind of the same as the other belt, but behind Neptune. So a lot of objects to detect there, and we still have a lot of work and a lot of information to have from them. Now the question is, okay, we have those rocks around us, but is it very important to watch them or not? Well, there is three main arguments to say we need to detect them and to observe them. The first one is that they are the relic, like a historic part of our solar system and its evolution. So if we want to have information about how the solar system was created and how it evolved, we can find those information with the asteroids. The second point, which is, I think, very important for every one of us, is the space awareness. We need to know if an asteroid will come to Earth or not, and if it's dangerous or not. And the third one is maybe later for the future, is that there is a lot of stuff in the SSO, so maybe we can like just mine them later and have more resources for us on Earth. I want to come back about a risk because, for example, this year, it has been announced that we were kind of lucky because one asteroid was detected as a big risk for Earth. And the problem was that it was a bit hidden by the moon. So they had to wait for a month to have more information to know if we were gonna have a big problem or not. And at the end, a month later, they were like, oh, don't worry. We did not tell you there was an asteroid coming, but finally it would just pass close to the Earth, but not on us. So good thing. But as you can see, this one was detected so lately that had no issue. Like we could not attempt to deflect it. It was not possible. It was over. So we really need to know what is around us. NASA is already doing it quite well, but even with this, we still need more information. So the more asteroids mission we do, the better it is for us. So now why Euclid? As I told you, Euclid is mostly a mission that will do deep space stuff, that are outside our galaxy and our solar system. And also I asked you to remember this picture, and there is one problem with asteroids with this, is that it avoids the galactic plane, the ecliptic plane, sorry, big mistake there. And the ecliptic plane is where there is the solar system, and the asteroids are inside the solar system. So can we really detect asteroids when we avoid the solar system with Euclid? Well, the answer is yes. The only SSOs we will detect is high inclination orbits, because of course there is asteroids going around the solar system, but you know, like going a bit up and down, not following the planets and stuff. So it's good information to have too, because it's not necessary asteroids we look at normally. So maybe we'll have new objects, we don't know. Maybe some stuff can be discovered via the Euclid images. Also, we might be able to detect some in the ecliptic plane, because for the calibration field, so when Euclid will be sent, we will first do pictures to see if everything is working accordingly, and it will be in the ecliptic plane, so we will be able to detect maybe asteroids in the calibration fields. But Euclid also is very precise, so we will have a lot of information about asteroids. So for example, rotation period, spin axis, orientation, shape. Also a bit later, but as we will have NISP, NISP is in infrared, and from a paper sent a few years ago, asteroids can be classified only if we use near infrared. So we have the visual of the asteroid and also the near infrared in the same at the same moment. So it's very nice to have all this information in one mission. Remember that Euclid was not made for SSOs at all. It was only for cosmology. So it's just like someone saw what Euclid was about to do, and he was like, okay, well, we have anything we need for asteroids, so let's do it. So it's a parallel mission, and now we want to do it with Euclid. Also for cosmology, as Euclid is using cosmology, knowing where are the asteroids in the pictures means that we will have less noise inside the pictures, which is nice for cosmology. So also it's nice to detect only for Euclid. We will have around 150,000 asteroids, which is still a huge amount of detections, so it's good for science. And as Euclid will be in the L2 point, if we do observation at the same time from will be the case with the LCST mission, then we'll be able to have the exact distance of the SSOs with using the parallax. Also, we have hour-long sequences. So with the distance and this, we can have a good information about the orbit of each SSOs, which is what we want in case of we want to send an alert for Earth. So more information about the position and the orbit of the asteroid. And also, apparently, Euclid is very precise, so we can maybe detect multiple systems of SSOs. So that's also a good plus for this. So a lot of reason to do it, but now we need to develop what we call a pipeline to do it. So a pipeline, in our case, will be like a block or multi-steps program that start from input data to have to achieve a certain goal. In our case, we start from level 1 data. We call level 1 data not the raw data, but just data that can be used for science, but are not yet cleaned, perfectly cleaned. Why we won't wait for clean data? Because, as I said, we want to send alerts very quickly. So if we detect an asteroid that might be a threat, we need to know the information as fast as possible. We cannot just wait 2 days to have the information. So we need to start from level 1 data and develop a quick pipeline to detect asteroids, so less than 20 minutes. In our case, we'll have a multi-steps pipeline. And the pipeline, what we call pipeline stages, will be, for example, one for cleaning the image, one for source detection, one other for astrometric solutions. So we'll come to that later. And at the end, we need a stage for the detection of the SSOs. So to organize the pipeline, you need to have a detection method, and then you organize your pipeline around the detection method. There have been a few developed the last years around the project of Euclid, and I will present you all of them. So I'm not an expert in each one, of course, because I was not working into them. I had to read papers and to discuss with these people to understand what they were doing. But I think it's interesting to see what is developed within ESA and with other universities in other labs to achieve this goal of observing SSOs with a mission that is not made for this. So the first one, of course, nowadays is to use machine learning and the very well-known convolutional neural network. So in this paper, the proposal was kind of simple. Normally, for example, with convolutional network, what you do is if you have cat and dogs, pictures of cat and dogs, the CNN, so the convolutional neural network, will be able to say whenever it's a dog, whenever it's a cat. Here, it's kind of the same question: is there an SSO image or not? So in this paper, this is what they do. They have a lot of pictures with and without SSOs. They train the machine learning algorithm, and at the end, they get those results, which are very, very good. It's a very good performance. It's very easy to detect an SSO or not in a picture. Only one issue is that it confirms whether or not there is an SSO in the image, but it does not directly detect the SSO. So if we provide a small picture with an SSO, then the machine learning algorithm will say, oh yes, there is one here, but we don't have any more information. So it's basic information, which is nice. It shows that CNN can be a tool, but we need more for the mission. But it's a first step. So another thing that was developed is to use strict data. I'm sure people from eSpace know this one because space awareness. So we use normally strict data to detect satellites around the Earth. And so the question was, can we also use that on Euclid data to detect SSOs? So in this paper, this is what they did. And the results are yes and no. So for specific asteroids, it works. So for bright asteroids with a very long streak, it works perfectly fine. Like you can see 96.9% of success. However, it's very specific, and in general, it's closer to 60% of detection, and there is a lot of false positive. So the strict data is nice, but it's not enough for our mission. So we need to find something else. So now we go back again to CNN. But this time, they want to do a whole pipeline using only machine learning to also detect and recognize the streaks of the SSOs. So as before, the solution they use is just to analyze the image like small part per small part. For example, 10 pixel by 10 pixel. So you scan the image like this, and then you check in each little picture if you have an SSO or not, because you cannot just send the whole picture inside the machine learning. As I showed you, it's enormous, it's a huge amount of data. So you cannot just throw this into a machine learning program and say, well, do the work. It cannot be like this. So you have to use a smaller part of the image one by one and then detect if there is an SSO or not. This is perfectly working as it was before, but now the problem is that streaks can be detected multiple times. For example, if there is one streak starting in top left and just on the right is still the same streak, how do you tell the program that it's still the same streak? So for this, they use the RNN algorithm. So RNN is normally used, for example, to complete one of your sentences. For example, if you say, hello, my name is, well, not name, it's not working, but to complete the of a sentence, you can use RNN. So they try to use like, because you have this information before in this image, maybe you can say that this information is the same. So they were working on this and the result is not very good. For now, they are around 60% again. So still some improvement to do. I don't know where they are now because last time we talked about this, it was a few months ago. And well, we have no news, so maybe it's not working very well. So now we come to the detection I'm working with at ESA, which use the more classical software from Astrophysics and Astronomy, which are Source Extractor and Scamp. So Scamp is also made by the same author of Source Extractor, and Source Extractor is very well known because it just extracts sources from images. It's being used in every space mission we know. It's a very powerful software. So we use Source Extractor to detect images. We use Scamp to align the images, so using the result of Source Extractor to align images. And then we try to find which objects are SSOs in the catalogs and which are not. In our pipeline, which is important to know too, is that we focus on very slow SSOs, which means that the streaks will be very, very, very small. Instead of the streak we saw before, CNN is very nice for this and maybe other software for very long streaks, but we focus on slow SSOs. So it's a bit, it's another challenge, and it is doable with Source Extractor because then it will be small objects. With a very long streaks, Source Extractor is not very, very strong. I wanted to talk about a bit the simulation we had to do because, of course, Euclid is still not out in space. So we need to have simulations of what Euclid will see. So you have a lot of teams working on this, how a galaxy will look like, how stars will look like. And problem is that the team doing that had never the time to simulate SSOs for us. So we had to do it like a homemade. It was before I came, so again, I did not really work on that, but I think it's important to understand that for now, the SSOs we are working on are very basic simulations. So maybe we will be lucky and we will have proper simulation just before the launch to be sure everything is working. But it's a bit of a mystery because, yeah, there is a lot of stuff to do, and now that the launch date is very close, I'm not sure we will be able to have the information we need. But we have 2 categories of velocities. We have 6 categories of magnitude. And so in one dither, we have around 2,000 SSOs. And we need then to work with that. Just to tell you, the SSOs are just to be simulated, just like stars, just being put aside. And then they do a small tray, and this is an SSO. So this is how it looks like. In this image, so you have the 4 dithers. You have the galaxy in the middle, one galaxy. And on the left and on the right, you can see a small SSO just going around, following the green arrow, which is what we simulated. So now what we want is to detect this object in each dither, and at the end, understand that this is a moving object corresponding to an SSO. And to give you a more general visualization of one CCD, it looks like with random SSOs in one CCD. So there is still a lot of object to detect. So I was talking about Scamp and alignment, and what we call is finding the astrometric solutions. What is this? As I showed before, Euclid will take 4 images that won't be perfectly aligned because they will be shifted to fill the gaps. So we will have 4 images that are not aligned. So we need first to align them. But even if we align them, the spacecraft is not very precise. We will know that he's somewhere looking somewhere over there, but not precisely where. And as we want to detect SSOs with a very precisely, we need to know exactly the coordinates in the picture. So what we do is we use the stars that are present in the image, and we compare those stars with stars we know, and we have the perfect, the precise position of these stars. And then this is how we use the information to know what are the coordinates of each object in the image from the stars we already know. So this is finding astrometric solutions. And you will see it's important because it has been mainly my work for the last month, is to find a software that can do that precisely. So as I said, you have a catalog of sources from your software that found all the objects in your image. You have the reference catalog of stars. Here we use mainly Gaia stars. And then we see in the catalog of sources if we have objects that could correspond to these stars, and then we just align everything, and we have the what we call the WCS information of the image. So Scamp, when I arrived, I had to work with Scamp to check if everything is working or not. And the answer was, well, no, Scamp is not stable at all. Sometimes we had problem with the memory. So Scamp is not very good with a huge amount of data. So sometimes we could just have segmentation fault coming from the program just because he was not able to work with this amount of data. And sometimes it was completely random. We don't know why. We maybe just copy a file, and with this file it's not working. Sometimes the data was not very huge, but Scamp was not working either. And we cannot allow ourselves to work with a software that is not consistent, especially for a space mission that will work for 6 years automatically. And so if suddenly we have half of the data that are not available because Scamp was not working, this is not what we want. So my part of my job was to find another way to do the astrometric solutions. So 3 propositions came. TweakReg, which is the software used in Hubble, so it proved that it could work. Astrometry.net, which is a software that is starting to be used in Euclid Consortium, and WCSFit. With TweakReg, I was working with someone on Hubble, but right now he's a bit busy. So the project with TweakReg is on a break. We had no time to improve it. But I had a lot of time to work with astrometry.net, and it was kind of funny, and I wanted to talk a bit more about this one because all the thing we have to think about how this kind of software works and how to develop the pipeline around it was very interesting, a bit frustrating too. And so this is why I want to insist a bit on this one. So basically, this one would just work with bright stars. So you'll try to find bright stars in your image. You find bright stars in the reference catalog you're using, and then just try to match them. So when we were using our images, then we have only 2/3 that were correctly aligned. At least a solution was found. And the other 1/3, no solution at all. And the question is now, why? What was I doing wrong with this software? It should work like if it works with one image, it should work with all other images. So what is the problem? Well, the first question is number of stars in one CCD. So I tried to count every stars in every CCDs. And the thing is that I was starting to see that under 18 stars, it was not working. So I was like, oh, maybe this is the solution. Nice. But then suddenly I could find 22 stars and it was not working, or even 25 here, it was not working. So apparently the number of stars is not the problem. So maybe it's the number of objects inside the image, and same thing, it was kind of random. So then I started to think maybe it's the between the number of objects and the number of stars. So again, I tried, and I had the same statistic as counting the number of stars. So nothing was changing. So let's try to find another solution. If it's not the number of stars, maybe it's the distribution of stars. So then I tried to analyze where were all the stars inside the images and try to compare in between working images and not working images. Here on top, the red means that it was not working, and on the green, it was working. And by just watching all the pictures, I could see nothing really, like, for example, a big hole or something like this explaining that it was not working. The distribution were kind of random and kind of the same for every picture. So it was not the distribution of the star inside the CCD that was the problem. Okay, so now what is the problem? Maybe the position of the CCDs themselves. So this represents the whole image, the 36 CCDs. The red ones are the not working CCDs, and maybe, you know, if it was on the top left, on the top right, or in the middle, or only on the borders, something maybe that could appear everywhere. And the answer is no, it was kind of random. And the left, you can see you have on the some CCDs not working in the middle on the left, and for the other image you have on the top left also not working CCDs, but also on the bottom. So again, it was kind of random, so no explanation at all. So what was the issue? Well, I finally found it's the brightness of the stars. So as I said, astrometry is working with bright stars, and what we forgot is that in our catalog we used what we call purge catalog, which means that the bright stars, the very, very bright stars inside an image have some faint, you know, like when you picture with too much light, you have those spikes coming out of the light. Well, you have the same with Euclid. And so those spikes can be taken as SSOs in our pipeline. So we just get rid of those stars and the spikes around the stars. So our catalog is missing bright stars. So why is it a mismatch? Well, on the bottom, you can see on the reference catalog, you have all those stars, and on the purge catalog, you have a few bright stars missing. So Astrometry will go inside the reference catalog. He will take 4 very bright stars, because this is how it works, and create a quad with it. So this kind of shapes. And he will say, okay, I have this quad, and I want to find the same quad in the catalog I have. So when he goes to the other catalog, well, the problem is we don't have those bright stars. So we take other bright stars and make another quad. And of course, have a mismatch. So in the pictures where we had too much bright stars, it could not be possible for astrometry to work. So what we do is that we don't use the purge catalog, we use the full catalog, and then it was working 100% of the time. Well, kind of 99.9% of the time. So way better. So now let's develop a pipeline around astrometry. So I had 2 ideas. The bottom one was not working because the function image to xy that you can see here was not working with our images, so we had to cancel it. But the top one, we start from a source extracted images. So we have the catalog of the sources inside the image. Then we use astrometry to try to align them using Gaia stars. Then we change the WCS in the images to have the image properly aligned. And then we use Sextratal again, but this time to exactly find SSOs, and then we can go on the pipeline. So this is what I did, but the problem is the result was not insane. So this is a way to check if the alignment is well done or not. So what we should have normally on very clean image is a beautiful peak and not very wide, and we want something close to 0.03 arc seconds, which means that an object is not further away from 0.03 arc second from other objects when you align the images. So the same object is kind of the same position in the 4 images. Problem here is that first, the precision is around 0.1, which is not good at all for Euclid. And also it's very wide. As you can see, there is objects that are very, very far away from the other position in other images. So it's not working at all. Well, it's working, but not good enough. So why? Maybe it's the simulations, or maybe it's astrometry the problem. So now we go to WCSFit and do the same job. We use WCSFit to try to align images, and we see what are the results. So here is the whole pipeline for WCSFit. So the first stage is clean the data. Okay, this is done. Then pipeline stage 2, we use these images and we try to find sources using a source extraction software. This time we don't use source extractor because WCSFit needs IMCore type of file, so this software to have the catalog. So we use IMCore. We have 4 catalogs. We use those 4 catalogs with Gaia stars and we send it to WCSFit, and then we try to align the images. Then WCSFit does the work, change the of the images, and we have 4 aligned images. Then we use source extractor on those 4 images to then try to detect objects, including SSOs. And then at the end, we have one last pipeline stage to only find SSOs precisely. Well, here are the results. It's way better. WCSFit can work with this kind of data. So it means that astrometry.net was kind of the problem. So now we just took the decisions 2 or 3 weeks ago to use WCSFit instead of astrometry.net. And now the pipeline is completely ready. And we just have to do more tests with new simulations if they come. And they can just use it when the Euclid will be sent. So it's kind of nice too for me to finish on a good point, having a proper pipeline working and not something kind of messy with astrometry.net. So yeah, I've been working on this for 2 years, and I wanted to talk about what I've learned from ESA and from my work. So first thing is adaptation. I've only knew the source extractor software before I came here, like in all the softwares I've been working for 2 years here. And so I adapt to a lot of new software. So how to install them, how to understand how they work, how to adapt the pipeline to the softwares, or to adapt the softwares to the pipeline. So it was kind of interesting and sometimes exciting, sometimes frustrating, but you know, it's adaptation. Also, on ESA, you work as a team. So you wait for data, or you need to provide data to others. So you have to adapt your way of work to all the teams depending on you and which you depend on too. It was my first work outside academic and in a space mission organization, like a big one, so, which is ESA. So I learned a lot about how a special mission is organized. And yeah, it's kind of interesting to know when you're inside, what are the decisions taken. Sometimes you're kind of surprised. So it was very interesting to know what was going on. And also how ESA is working, because from my point of view, from a very, I would say, naive point of view, ESA was a lot of scientists being all together very happy to do science. But it's not really, ESA is more about administrative and how to handle teams working then on the science. So it was very good for me to understand how ESA was working, and then how I could help this and where I want to be in this big chain of space science. Also, I was a bit working outside my field. Normally, I'm more into dark matter, dark energy. This is why I like Euclid. But then I was going to work on planetary science, which I never did before. So it was very nice also to just go a bit of the field I like to discover new things and how it works in other fields. So very interesting too. And finally, of course, from all the new softwares and everything I had to do, I have now new skills that I think will be very helpful for later, for the future of my profession. Also, my personal evolution in the project. So I started as, you know, with COVID and stuff, just reading papers, testing code, everything was going a bit slow. So it was interesting, but, you know, at the like, okay, I'm just the new guy, the new young guy, just trying to do stuff. Maybe what will happen after the 2 years? Well, as I finished, I'm kind of very happy of the work I could do. I could develop new pipelines, just not test one, just develop new ones from the early ones. So very cool. Now I'm kind of beta tester of an important project for pipelines, which is called Pipeman. That will be used in whole ESA for a lot of space missions. So I'm directly connected to this project and I'm doing tests on it. And also in the Euclid consortium, we still haven't chosen the program we want to use officially in the different pipelines of the whole mission. And so people are coming to talk with me about what I think of all the software I used, how we should use them, etc. So it's also nice to feel that now I'm part of the team and I can discuss with them and give advice or learn stuff. And I feel I'm part of the Euclid team. So it's very nice to end like this the internship. I've been talking a lot about work, but not only work. YGT's program is also about meeting new people. So I met a lot of amazing people, I would say, from other countries, Canada, Spain, Germany, Sweden, France, etc., etc. It was very, very cool to meet all those people, to just have fun together sometimes, playing cards or going out in Madrid. So also, there are young people at ESA, and it is very interesting and very nice to meet them and be with them. So what I would say, the last words is try the YGT program if you can. If you just finish your master, try to apply. You won't regret it. It's very nice. And we need, if you're Swiss, we need more Swiss people in ESA. So please come and represent our beautiful country in a space mission, because we are good and we need to show it. So thank you for your attention. If you have any question, please ask.
Thank you very much, Aurelien. So I think there was a question in the chat from Belen, and it was referring to slide 32, I think. And the question is, what's the time delay between the 4 exposures?
So between the 4 images, it's around 1,000 seconds around. I think I showed it here. So in between each dither, there is around 1,000 seconds.
Okay, thank you. And I think Claude has a question. I'll just unmute him.
Yeah, do you hear me?
Yes.
Okay, thank you very much, Aurelien, for a nice presentation. That was really, really good. Congratulations, and also thank you for sharing your thoughts about working at ESA. Of course, worked at ESA for quite a while. I didn't do too much administration, and I was in a world where administration was very far away, but I guess it depends on which sector of ESA you work on. I have a question about the sky map that you showed about what Euclid is observing, and these are the colored areas. Yes. And I guess this is a map on with the horizontal line in the middle being the ecliptic, is that right?
Yep. Yes,
okay.
The middle, yeah.
And the other one is around the galactic equator, is that right?
Exactly, yeah.
Okay, now I understand why there's exclusion around the galactic equator, because you want to look at extra galactic objects, so you don't want to look through the dust and gas inside the plane of the galaxy. But why do we have this exclusion around the ecliptic, the eclipto along the zodiac in a way? Why do you have that?
So first there is the sun. That you want to avoid.
Yeah, I understand, but except the direction of the sun, there's a whole rest of the area where you could observe, no?
Yeah, so from what I've read, so it's been a while, but I think just that we really don't want any kind of, as we want to do cosmology, you really don't want any artifacts inside your images. You want to have precisely what we should see outside our galaxy. So the problem is with those asteroids, with all the thing you could have going inside the solar system, it could create artifacts that, because we now detect SSOs, but at first Euclid Mission was not about to do it. It was just looking at the sky and then directly work on these images. So we will help a bit detecting those artifacts with the solar system objects, but Euclid is not made for this. There is not a pipeline or anything else to just filter everything in our solar system. So we really want to avoid any artifact to be sure we are looking at cosmologic objects.
Okay, I understand. So they want to avoid artifact because there would be an asteroid, another object that would disturb the observation of objects in the extra galactic world. Yeah. And of course, we avoid also the plane of the galaxy for not artifacts, but just the dust and
exactly.
And gas. Okay, I understand.
Yeah.
Thank you. So in a way, they block the region around the ecliptic, which you would like to have, but of course your objective is not the primary objective of.
Yeah, exactly. We cannot ask
Okay.
them to change the whole mission for us.
Okay, I understand. Well, that's quite interesting. Thank you very much.
Thank you.
And we have questions in the room here from Stefan, our colleagues.
Yeah, thank you very much for the interesting talk. I have actually a few questions concerning the, at one point you said that you are going to also like interpret the data in terms of trying to estimate rotation property, rotation periods and other properties of the objects. So, but I mean, this requires a lot of observations for each individual asteroids. Did you check how often you expect to observe each individual asteroid, or are you trying to combine your data set with other available data sets?
Yeah, so this is still on the work also, because we'll say that the mission started, like the idea to detect SSO started like 5 years ago, something like this, even more. And with what Euclid was proposing, with the hour-long observation of the sky, we would have a lot of information about the SSO we detect, because it's very long observation time. So from those observation time and the very precise, like Euclid will be very, very precise. So with the small amount of changes in light or anything will give information about the asteroid itself. The thing is, for now, this is just purely theoretical, talking about the precision of Euclid. We still are just trying to detect them, which took a lot of time because COVID made everything slower and stuff. We should be at this point right now, if everything went well, try to actually show that we can do it now. But however, we'll have to do this in the next month and maybe wait for Euclid data to show that it was possible. So because Euclid will be very precise, we think it's possible. But for now, there is nothing done to actually detect this.
Okay. So, and what's the exposure time of each individual dither image?
It's 1,000 seconds.
1,000 seconds. Okay.
Around here. It's changed a bit every time, but it should be around 1,000.
Okay. Cool. Thanks. So, and concerning the plate solving, you said you were using astrometry.net in the first place, but you were not really satisfied with the results by this.
Yep.
You changed to, I don't know what other method.
WCSFit.
Yeah. So do you know what kind of solution astrometry.net in the end used? So did you just use a linear solution for the whole frame or for each individual CCD, and then maybe the other version or the other method was using a higher order solution, so that this in the end gets much more precise? Or
so for astrometry,
yeah.
what I know, because I've read a lot of papers because of this, is that, as I said, it's using quads built from bright stars. So what it does is that it's trying to matches these quads. So I don't know if it's linear or exactly if it's linear or not, but I think the problem is as it's very bright stars, you don't have the exact center of the star. You know, it's very bright and very large. So maybe astrometry will take the center of the star a bit here or a bit here. So the quads will be a bit moving depending of the brightness of stars. And so this is why it's not precise enough at the end. So one test we wanted to do is to maybe don't use very bright stars, only the less bright stars. But then the problem is that you might not have enough stars and stuff. And even with this is how I managed to get like 0.09 instead of 0.093. So even doing this, we still haven't a good solutions for this. So I think the problem with astrometry is using the exact position of bright stars, which is a problem because where do you put the center of the star at the beginning?
Yeah. Okay. Thank you. So maybe an idea would be to because like start with bright stars, because then it's easy to recognize the patterns. You don't have to correlate so many sources, and then have an iterative approach and consider fainter and fainter stars, and then disregarding the bright ones, because the errors of the bright ones are, as you said, too big.
Yeah, that was one of the idea, but as I had not huge amount of time, and I wanted to be sure it was because of the itself and not the simulations. I tried WCS and it worked perfectly fine. So before I leave, I wanted to do something working. So this is why I just went to WCSFit. But yeah, the next month, like there is some people still working on this the next month. They could do that because this is still something we could do, yeah.
And then final thing was, yeah, so you're going to discover a lot of asteroids with Euclid, I assume. And these discoveries need follow-up. Are there already any plans for like ground-based telescope network, or are you working together with like the optical ground station from ESA, for example, to do the follow-ups, or are you?
So there is a project called Think, F-I-N-K, I think, Think or Flink. Every time I don't remember if there's a L or not. And Think is a big database that try to take every information that are, for example, pulsars or stuff like this, just a very timing event in space. And we have a collaboration with them, and they will the data from our pipeline. We'll send the catalogs to them, and then they will work with it. So yes, the data will be sent to a group that will be there to use the data.
And are they doing follow-up observations? I mean, once you have discovered the object.
Yes, there is a LSST in development right now, which is a telescope that will be built. I don't remember where now, but it will also do the same as Euclid technically, but from Earth, like the same areas. And so, and in the south will be some missing areas, of course, but still some common areas. So at least with this telescope, it will be possible to match to see where was the asteroid after. And you have a lot of other missions, and I hope at least, that Think has also connections with other telescopes around the Earth and maybe ask for a specific observation because of one asteroid we detected.
Okay, thanks.
Any other questions in the chat, or if someone wants to raise their hand? If not, then I think we can finish now. And I want to say thank you to Aurelien again.
Thank you.
And well, thank you so much to everyone for joining. This talk is recorded and will be posted on the YouTube channel of eSpace. So if you want to watch it again, you can go there. Thank you very much again, and I'll see you for the next seminar, which will be in December. There's no date yet, but stay tuned on our social media so you can keep up. Thank you very much, and see you soon.